Hi, welcome. We're going to have a quick lecture today on power, centrality, and hierarchy, and specifically on some ways that we measure these when we look at networks. Next week, we're going to talk more about kind of the theoretical ideas behind what it means to have sort of network power and some more kind of theoretical and sociological ways of considering these ideas. So I can't help but start with a dad joke. Bro, can you pass me that leaflet? Bro, sure. Like usual, pretty bad, but there we are. Okay, so what does it mean when we think about power in social networks? Well, we'll talk a lot more about this, but this idea of power has a long history. One version of this is that it's the capacity to achieve your will, your ability to meet your goals, right? That is power. People who have power get what they want, both for good or for ill. And how do we do that? Again, we'll talk a lot more about this, but through capital. So you've probably heard the term, and we've used it in class already, social capital, that we can think of social networks as having social capital. And this is, the idea is that through we can sort of activate the people we know to use their abilities and resources to help us in order to meet our goals. So who is it? Who has power in a social network? Who is most likely to be able to use their connections and the resources of their friends and acquaintances in order to meet their goals? And I want to step back for just a second. Again, we'll talk more about this, but this seems very Machiavellian maybe and cynical. I think that it's possible to think about these as really good goals, right? That we can meet our goals to make a better world, to spread information and knowledge, etc. That this doesn't have to be, that how do we obtain money, power, fame? How do we, crush those in our way, etc. That power doesn't necessarily have to be negative. So with that caveat. So how do we measure it? Who has power in a social network? And I'm going to talk about a few of the most common measures that are used when we're thinking about this. The simplest, oh darn it, it's not showing the bottom of my screen. Hold on a second, let me see if I can adjust that. Oh, darn it. Okay, I'm going to pause for just a second, fix it, and come right back. Okay, I am back with a fixed slide. So this is the karate network that we've seen a few times already. This is a real-world network of karate students and their friendships. Pretty sure it's friendships. And so how might we measure who has power in this network? Who would be most likely to be able to, for example, persuade people to I don't know, vote for the person that they want to vote for, or something like that. And the simplest version is degree centrality. This is maybe where our minds would go first. And this story of these measures is sort of a story of increasing sophistication and realizations of weaknesses of one measure and strengths of another. So this is sort of where we might go first, is who has the most friends? Sort of a popularity contest, right? Popularity, as we all know, popularity can be a form of power. And so if we look at this, this is called degree centrality. And it's really just a count of the number of edges each node has. So so in degree is, sometimes popularity. So for something like Twitter, this would be like how many people follow you. Out degree is something more like sociability. How many people do you follow? How many people do you go to for advice, for example? Or it can be all, which is sort of what it is the default when it's undirected like this, or we just add up all of the degrees. And so in this network, we can see it actually cuts off, but you can see out of the first few, number 1 is by far the most popular, right? They have 16 edges. And you can see 34 and 33 are also very popular. it cuts off at the bottom, but they're probably are in the same ballpark. So that's the simplest version. This has some downsides, though. One of which is let's talk about it. Is how that if you're sort of way off in the corner with your little group of friends and you're all friends with each other, you might all have a high degree of centrality, but are you really important to the whole network? And so one version of trying to fix this is called closeness centrality, which is the average distance to all the other nodes. So if you look at this, I want you to take a second to predict which ones you think will have the highest closeness centrality. So take a look at the graph, pause the video for a second, and I think it's really worth taking the time. Which ones do you think will have the highest closeness centrality? I'm going to show you by size which ones do. Okay, welcome back. So the answer is, in this case, the ones in the center, right? That these network, spring-directed networks, like the one that we have here, where they kind of clump together people that are connected to a lot of people, are actually a pretty close approximation of closeness centrality. So the ones who are in the middle are pretty close to a lot of other people, right? Whereas those on the periphery, so for example, all of these, 24, 28, 29 even, have quite a few connections, but they're sort of far from the nodes that are way over here, 22 and 18 and 13, and very far from 17, who also is very low closeness centrality. Whereas all those in the middle, 9 and 20 and 14, maybe don't have a ton of degree centrality, but they're right in the middle of things. And so this is, on average, so there's this concept of distance, which we've probably mentioned a little bit, which is how many hops is it basically to the other nodes around you. And so from 9 to 34 is 1, 9 to 23 is 2, right? It takes 1, 2. And 9 to 26, I'm not positive I could find the shortest one. So this is, the way you do it is the shortest one, right? So maybe 9 to 3 to 20, maybe it is that far. 9, let's see. Oh, there we go, to 33 to 32 to 26. So that's 1, 2, 3. And so what you do to figure out closeness centrality, and you don't actually do this, right? The computer does it for you, but adds up all of the closest, like how far is it from you to each other node in the network, and then just averages those. And so if yours is really low, then you have a high, sort of the inverse, a high closeness score. The next idea is betweenness centrality. So this one misses out on the idea of structural holes, which we've talked about, that there is an amount of power that comes from bridging two groups, that if you happen to be in a middle group that's close to everyone, that's one kind of power, but that misses out on brokerage, which is the idea of being in a structural hole, right? That you're in the middle of two groups, and so you have this opportunity to kind of broker what information makes it from one group to another. And so that's betweenness centrality, is trying to measure this structural hole. So again, I want you to look at this and predict. I'll size the nodes again based on betweenness centrality. Predict which ones you think will have high betweenness centrality. And again, I'll give you a second to pause the video. Okay, welcome back. And so here's the answer. When it comes to betweenness centrality, 1 is really high, right? Because 1 is actually the only way that all of these nodes down in the bottom right, I guess show you over here without my face blocking too much of it, all these nodes in the bottom right only make it to the rest of the network through 1. So 1 has this huge amount of betweenness centrality. You can see 32 is maybe a little higher than we would expect as well, because they're connected to these, which are only connected there. 34 and 33, unsurprisingly, they're the only ways that sort of this group are connected to the network. So this, again, that tries to capture this other notion of power of being in a structural hole, of connecting people who would otherwise not be connected. Again, there's some weaknesses to that approach, just as with any of the others. The measure of eigenvector centrality tries to capture that the idea that it's not what you know, it's who you know. In other words, a connection is more valuable if that person is connected to a lot of people. And so this tries to sort of capture this idea of like power diffusing through a network. So if you are, for example, connected, I mean, the example I gave class that I always give for this is if you only have one friend, but your friend is the president, then you still have lots of power in the world, right? And so that it's their power sort of extends to you. And so that's the idea of this. An eigenvector is, you don't need to worry too much about the terminology. It's a very confusing name, but it comes from like that matrix algebra that's used to figure this out in order to make these measures. And so here's the eigenvector centrality. In this network, we see a lot of the same sorts of dynamics that we've seen in the past, right? 33, 34, and 1 are all really important. We see that 3 is actually almost as important, I mean, really pretty darn close to important as them, even though 3 has far fewer connections, because 3 is actually connected to both 33 and 1, right? And they are both important in the network. And so 3, by having 2 really important friends, gains power themselves. You can see how this sort of diffuses, right? That there's lots of power in the middle, and we see it sort of taper off as you get toward the periphery. As with many centrality measures or measures of power, that being central, there's a reason we call it centrality, right? Is often when we try and plot these things, the people who are central, who are sort of in the middle of things, often have the power in a network. And I think that's pretty intuitive, and I think it's true. If we think of who has the power to move an organization, of who has power to influence people, it's the people who are kind of connected to a lot of others and connected to the important others. This sort of, I'll give another brief aside, this sort of structure with a small group in the core of a network that are all tightly connected to each other, and a larger, usually larger, but a large periphery of folks who are connected kind of to one or another of the people in the core is very common. It's very common. I think we can think of a lot of reasons. You can measure it think of it as some sort of like devotion to a group, for example. This is a karate network. Maybe these are the beginners who are just starting out, who are sort of the once a week people, and these are the people that are at the gym every day. You can think of lots of reasons like that. But this sort of structure is just really very common in real world networks. Okay. So that's the idea of centrality and power at the individual level, like at a node level, if you want to think about who has power. There's a related concept called centralization, which is sort of I think you can call it, I forgot to talk about density first. But I think centralization is the key idea that ties these two together, is that centralization is this idea of how distributed is power. Do most people have about the same amount of power in the network, or is it really one person has way more power than another? So there's a few sort of network level measures that we use to try and get at some of these questions about what does the whole network look like. The simplest, and I do want to bring it up here, is density. So this, I know this math may look a little scary. This just means sum. So the sum of the edges, so count how many edges there are, and divide it by the number of nodes. So n is the number of nodes, multiplied by n minus 1. So the idea is, like, let's say, if you have 4 nodes, right, 4 times 3 is 12. This is the number of possible connections there are, because each of the 4 could be connected to the other 3, right? So that's where the 4 times 3 comes from. And then you count how many there actually are of those 12 possible edges in a directed network, how many of them actually exist. If there are 6, then you have a density of 0.5, for example. If it's an undirected network, then you multiply that by 2. So with our 4 nodes, if it's an undirected network, there are actually only 6 possibilities, right? Because if there are 12 possible edges that are directed, we can imagine that means one from node A to B and one from B to A. So you just divide that in 2, collapse those into one edge. So thinking about the other way, you can multiply this formula by 2. But that's all. I got way too mathy there. The big idea is this is the proportion of possible edges that actually exist. That's density. How dense is the network? It goes from 0 to 1. Human networks, really depends on the scale. If we think of like all of humanity, I mean, it's incredibly, incredibly sparse, right? Not very dense at all. 0.0001, I don't know. That there's so many possible connections between the, billions of people in the world that the number of actual connections is vanishingly small. But in some, if you look at a smaller, like within a fraternity, for example, it might be fairly large. Okay, centralization. This is the concept I talked about before. The idea is how unequal is the power. Does one person have the power, or is it sort of equally? And so I show 3 different networks, and this is just a random network, a star graph, and a ring graph. And so here's between this centralization, you can sort of actually measures of centralization for any of the centrality measures that you want. It's sort of just, how spread out is the power. And so this random network has a centralization of 0.2 about. You can see that some of the nodes have quite a bit higher between a centrality than others. A star network has the maximum centralization of 1. So it's intentional that I chose that. One node has all the power compared to the others, and a ring is, or a lattice, both of those have centralization of 0 because every node is identical. They're really interchangeable, and so that's the idea of centralization. Finally, one other concept that I think relates to this is hierarchy. I'm using a different network here because hierarchy can only be used for directed networks. So this is an advice network in a high-tech firm. It was high-tech. I think it's from the 80s. So who do you go to for advice? This is what the advice network looks like. And the idea behind hierarchy is sort of thinking about how information flows, in this case, advice flows. Is it something that's sort of circular, right? That people get advice from all levels, or is it something that's sort of top down? And so what it measures is, can you get, you can think of it like a flow, right? If you can get from node A to C, however it is, you go from A to B to E to C, can you also get from node C back to A, right? It's directed, so you probably can't go back the same exact way, but is there another path back? So it's just a measure of what ratio of those people you can get to one direction can you get back the other way. So sort of a nice measure of how well do things flow in a network, and how top down is information. I think that's it. Yeah, that's all I wanted to share with you. Hope that's helpful. Look forward to talking about these ideas in class.